Hello and welcome to another video. I'm going to talk about optimization, which in most cases will require using the derivative, but not necessarily. Let's start off with this problem. A company is planning on producing a cylindrical can, and I know the volume. It has to be 330 cubic centimeters. Now, I'm going to build what's called a mathematical model for the surface area depending on the radius of the base. Now, here's actually what the volume of the cylinder looks like. Pi times r squared times the height. Here's the cylinder. So this is how we calculate the volume of the cylinder. Great. Now, I know that the volume is going to be 330. So this is like my equation for the volume as it's set up. Now, what's going to happen here is that I want a mathematical model for the surface area depending on the radius of the base. Now, let's leave this here, this expression with the volume here for a minute, and let's figure out what the surface area is going to be. Now, the surface area is going to be this, 2 times pi times r times height times 2 times pi r squared. Now, why is that? Well, let's look at our can. Let's actually open up the lid, cut through it, and open it up and leave it flat on the ground. This is what it looks like. Now, this circle here is pi r squared. Clearly, you can see that, it's pi times r squared is going to be the area of this thing and the area of this thing, which is why I have 2 times pi r squared. And this rectangular part here is going to be the height times 2 pi r, because this side here is going to be 2 pi r, which is the perimeter of this circle here. So that's why I end up with 2 pi r times h plus 2 pi r squared. And that's going to be an expression for the surface area. Now, combining these two formulas, I can actually have a mathematical model for the surface area depending on the radius of the base. So first of all, I use the volume equation and I put the height in terms of the r. So if you tell me the radius is 4, I calculate the height for a volume 330. If you tell me the radius is 1, I calculate the height for a volume of 330, and so on. Now, we substitute this in the equation wherever I have the h, and this is what I'm going to end up with. And I can clear this expression out, and this is what I end up. Now, this thing here, and this is important, is a mathematical model for the surface of area depending on the radius of the base. So you tell me the radius and I give you the surface area for a can that has a volume of 330. Let's go through the implications of a mathematical model once more. Now, what exactly is a mathematical model? Here I have a mathematical model for the surface area of the equation depending on the radius. So, the surface area of the cylinder depending on the radius. The volume has to be 330 cubic centimeters. Now, the important thing here, again, if I say the radius is 2, I'm going to get that the surface area must be 355.13. If the radius is 5, I'm going to get this. If the radius is 3, I'm going to get this. So depending on the value of the radius, I'm going to get a different surface area. That's great. Now, here's an important thing. Is this exact? This is really how cans are. Like, what's the point of this? Because cans, again, might not be exactly cylindrical. Maybe there's a small manufacturing error here and there. Now, this is important. Reality is always more complex than the mathematical model that you use. But it's just a very good approximation that allows you to make some calculations to analyze the complex reality in a more efficient way. That's what a mathematical model is. This is exactly what we have here. Let's use a derivative. Let's do some optimization here. I have here my mathematical model for the surface area depending on the radius of my 330 cubic centimeter can. Now, I can even plot this if I wanted to. But I'm not going to do that. I'm just going to make the derivative here. Here's the derivative. Remember that this is the same thing as 660 times r to the power of minus 1. And I can just calculate when it's going to be 0. Because, hold on a second, if you think about it, when the derivative is 0, I'm going to have a minimum point. That's going to be the point for which the surface area is minimum, the smallest. That means that I'm going to have the same volume, 330 cubic centimeters, but the surface area is going to be as small as possible. So I'm going to use the little material as I can, which is great because it's going to be cheaper. Now, I can solve for r, and this is what I'm going to get. approximately 3.745. So the radius of the base of the can must be 3.745 if I want to do it using as little material as possible to get a volume of 330 cubic. Here's another exam exercise. Profit made from a car model sales comes from two sources: 8,000 euros for the manufacturing cost per unit, and they get sold at 15,000. So the profit I'm making there is clearly 7,000. And of course, I pay employees bonus. Units sold per month, I square that number, and I give I multiply it times €1, and that's the employee bonus. So what is the optimal numbers? Because clearly, if I sell a lot, I'm going to be paying a lot of employees bonus. So we define a formula. Here it is. It's going to be 7,000 times x minus x squared. And that's going to tell me for x number of cars sold, how much money I'm making. Now, I can find the maximum point of this function by simply making the derivative and putting it equal to 0. And I get that x is 3,500. So what does this mean? It means that selling 3,500 units per month is the ideal production rate. Like if I sell more, I generate cost and employees bonus. If I sell less, I'm not making as much as I could be making. So that's how optimization works. Thank you very much for watching. See you next time. Goodbye.